Okay, here's 5.4. So this section is partially about indefinite integrals. So this is an indefinite integral. What makes it indefinite? We've seen things like this before. They typically, when we saw them before, it had a number from here to here. And this does not have any numbers written there. What we did before was I would take the antiderivative of this function, and then I would plug in the top number for x and the bottom number for x, and I would subtract those two answers from each other. When it doesn't have, okay, let me start over. Those are called definite integrals. When it has numbers here and here, that's called a definite integral. This is an indefinite integral when it does not have numbers here and here. What this means, an indefinite integral, just means you're going to find the antiderivative. And you're not going to plug in anything in because you don't have numbers here. You're just going to find the antiderivative. And when we say the antiderivative, we mean the most general antiderivative, which means you have to put plus a constant. So your answer for this should always have plus c at the end. Sometimes we use a different letter other than c, but usually we just use c for the constant, and you should always have plus a constant at the end of your answer. So let's do one like this, and obviously I mixed together a large number of things here. But we know that we can just take this apart. To do the antiderivative of all of this, I just have to do the antiderivative of this part, plus the antiderivative of this part, and so on. So let me get going. The 3 comes right down, and then I look at this. This is a power of x. What you do is you increase the power by 1, and then you divide by that new power. So of course the 3's cancel. I can do that right now. Here I can do the same thing, because of course this is x to the 1. The 2's cancel. This is 1 over x, which is the same as x to the minus 1, right? Now, in the book, in section 5.4, you'll see a table of antiderivatives of common functions. This is a power of x, x to the minus 1, but we don't treat this like other powers of x. X to the minus 1 is special. If you think about it, if I did the same thing with other powers of x, it wouldn't make sense, because if I increase the power by 1, the new power would be 0, but then I have to divide by the new power, so I would be dividing by 0. So I really can't treat x to the minus 1 the same way that I treated x squared or x to the 1, or the way I treat other powers. But this is just in the table. The antiderivative of 1 over x or x to the minus 1, they're the same thing. The antiderivative is natural log absolute value of x. The absolute values are important in case x is negative. You can't do the natural log of a negative number. But with these absolute values on there, you can basically do whatever you want, except x equals 0. You still can't do the natural log of 0. And then for the rest, we have to keep looking at the table. Secant squared x, the antiderivative, if you see it on the table, it would be tan x. Right, also, we know that because we know the derivative of tangent x is secant squared. That's a more familiar fact, and therefore the antiderivative of secant squared is tangent. What do we have here? Well, the 3 can come right down, and then the antiderivative of 1 over x squared plus 1, that's arctangent. And this is just from the table. And this is also something that we knew before. The derivative of arctangent is 1 over x squared plus 1. So there it is. I'm basically done, except for one thing. I should remember to put plus c on my answer. And maybe I should write my final answer a little bit cleaner so it doesn't have this canceled 3 and the canceled 2. But so this is just a lot of writing now. but I'll call that my final answer. Okay, so there's ones like that where you just have to look at them. You just have to look at the table. It's possible that you'll have to do a little bit of algebra or something first. Then there are examples where on the online homework they'll tell you or they'll give you an equation and then you'll have to check whether it's true. It's either true or false. And you want to check it by differentiation because you're not going to get something that you can check using the table. What you have to do is to check if we're claiming that the antiderivative of this is this, then what I should do is I should take the antiderivative of this side and check whether I get this. Right? So I'm going to take this. This, I just have to use the chain rule. The outside, remember this is like parentheses around the sign and then squaring it. So the outside function is squared. So the derivative, I would do 2 sine x to the 1, because that's like I took the 2 down and now it's a 1. And then I have to multiply by the derivative of the inside. The derivative of sine x is cosine x. Of course, the derivative of c is just 0. In fact, I didn't really need to carry this c down. This part is always going to work out. The derivative of the constant just drops out and it's 0. So I get 2 sine x cosine x. And what was I doing? I was taking the derivative of this and I was checking to see if I get this answer. It doesn't look like I did, but I did. And this is very relevant to the online homework. There's trig identities. Sine of 2x is 2 sine x cosine x. Cosine of 2x is cosine squared x minus sine squared x. So this one is relevant to this problem. So this is the answer we got, and it's the same as the answer that we were checking it against. So I would say this is true. On the online homework, you may also have to use this trig identity. So watch out for these ones. You might find yourself checking something by differentiation and it involves a trig function and the answer that you get doesn't quite look like the answer you expect, but it might still be the same because of a trig identity. So really check your trig identities to see if it's true. Okay, what do we have other than that? We have some questions in this section about velocity and acceleration, and this is not entirely new, but, well, okay. I'll talk about this when we get to part B and C. Part A is nothing really new here. What you need to know is that if you have the position function of a particle or an object, the velocity is the derivative of that, and the acceleration is the second derivative of the position function, or you could also say it's the derivative of velocity. So velocity is the first derivative of position, and then acceleration is the derivative of velocity, which is the second derivative of position. So anyway, here we're given the acceleration function over a time interval, and then we want to find the velocity function. Basically, I'm just going to do the antiderivative because acceleration is the derivative of velocity, so velocity is the antiderivative of acceleration. And now that I have this notation for antiderivatives, I can write it this way. So this is just the antiderivative of 2t minus 8. And then this would be t squared over 2, because this is like t to the 1. And then the antiderivative of 8 would be 8t. The antiderivative of a constant is just that constant times t, or times x, or whatever the variable is. Now I should put plus c, because as always, I have to. And of course these 2's cancel. And for this problem, we should be able to figure out c. You should check whether you're given any specific information that would allow you to figure out c. Typically, that information comes in this type of form. It tells you v of 0, or it might possibly tell you v of 1 or v of 2. Usually it's v of 0. But what you do with that information is, now that I have my answer, or I have like a partial answer, all I have to do is figure out c. So I'll call this my partial answer. I'm going to just plug in whatever this is. They told me v of 0, so let me find v of 0. According to my formula, if I put in 0 for t, I'm going to get 0 minus 0 plus c. Meanwhile, v of 0 is supposed to be 7, so that just told me that c is 7. Now let me update v of t. Now I have my full answer, not just a partial answer, because now I know c. So that's v of t. And if I want to be a good physicist, I'll state the units. This is in meters per second, just because, well, the acceleration was in meters per second squared, so velocity should be in meters per second. Okay. Let's talk about part B, the displacement over the interval. Displacement literally just means change in position, and that could be positive change or negative change. Your displacement can be positive or negative. So, well, without making this too complicated, the displacement is just the integral, and this we're told to do from t is 0 to 10. It's the integral of velocity. So we can just do that. I would get 1/3 t cubed minus 8 t squared over 2 plus 7t. And since this is a definite integral, I don't need to write plus c. I have numbers to plug in, so I'll just plug in those numbers. So I will get, oh boy, this is kind of big, 1,000 over 3, this is just 4, so 4 times 100, or whoops, minus 400, plus 70. And why don't we get a common denominator? I don't want to be lazy. 1,000 minus 1,200 plus 210. So actually, in the end, it's not that big of a number. I get a negative 200 plus 210, so that's just 10/3. And it should be in meters. So why was the displacement so small? For part C, we're going to talk about something slightly different, the total distance traveled. Now that sounds like it might be the same thing, because I told you displacement is how much your position has changed from beginning to end. That sounds like distance traveled, but there's a subtle difference. Um, if I start here and then I go all the way over here and I come back, my displacement is 0 because from beginning to end, my position has not changed. But if I do the same thing, I go here and back, my total distance traveled is just whatever the distance is from here to here, and then the distance traveling back. So the distance traveled would not be 0. The distance traveled would be this distance plus this distance. Well, I guess it's twice the same distance, right? So here's the issue. This object that we've been studying the motion of, sometimes the velocity is positive and other times the velocity is negative. So this did move in one direction and then move back in the opposite direction. So what we have to do is we have to count all of that. So let me, first of all, what we're doing is this. This is the difference between the formula for total distance traveled and displacement. Is for total distance traveled, I put this. For displacement, I put this. The only difference is the absolute values. That's the only difference. And what those absolute values do is, with those absolute values there now, it's not going to matter whether I'm moving in the positive direction or the negative direction, because the absolute value just makes it all look positive. And then so what that does is, if I go here and then back, it doesn't cancel out. It adds up all of the distance that I traveled. So this is what I'm trying to do. And how do I take care of these absolute values? What I have to do, these absolute values make everything pretty awkward. It's not that bad. We'll be able to do it in a few minutes, but it makes it significantly more awkward than before. What I have to do is I have to figure out where this is positive and where it's negative. So first, let me set this equal to 0, and luckily I gave us one where t minus 1, t minus 7. So t would be 1 or 7, and then I can make a little number line. I'll write 1 and 7, and then maybe since we're interested in the interval from 0 to 10, I'll mark 0 and 10. And then maybe I'll just put a plus or minus in each one of these spots according to whether this is positive or negative. So for t, like maybe if I just put in t equals, well, I guess I shouldn't put in t equals 0. I should put in something in between. Say t equals a half. If I put that in here, I'm going to get a negative number times another negative number, so that would be positive. If I put in some number in here, like say t equals 2, I would get 1 times negative 5, which is a negative number. If I put in a number here, like say t equals 8, I would get a positive number times a positive number, so that's positive. Okay. Now here's what I can do. This is, I'm going to break up the integral at 1 and 7. So first I'm just going to do the integral from 0 to 1. In that interval, I just drop the absolute values because I've determined that this is already a positive number on that interval, so the absolute values weren't doing anything. Plus, the integral from 1 to 7, that's my next piece. And I'm going to go until I make it all the way to 10. So for my next piece, this function was negative. So what does the absolute value do to a negative number? It switches signs. So here's one way to algebraically represent that. I just put it in parentheses with a negative in front. Keep in mind, on this interval, this is a negative number. So this negative sign makes it a positive number the way it's supposed to, because the absolute value is supposed to make it a positive number. Don't be fooled by this negative sign. This negative sign is making it positive, because without this negative sign, it would be negative. Okay. Plus one more piece, the piece from 7 to 10. That piece is like the first piece. The function is positive on that interval, so the absolute value doesn't do anything, so I just drop the absolute value. So those are the two things that can happen. You break it into pieces, and on some of those pieces it will be positive, in which case you just lose the absolute values, and other pieces like this one, it will be negative, in which case you can just use parentheses and put an extra negative sign, and that extra negative sign is what makes it positive. Okay, and I did not leave myself enough space, so let me give myself another piece of paper. So I have to figure all these things out. Actually, I'll try to be efficient about this. Let me call this one, say, X, this one Y, this one Z, so I don't have to write all of this again. So the one I'm calling X is, okay, so I'm looking at this, and I don't really need to write it again. I can do the antiderivative. This is 1/3 t cubed minus, actually, I already did all of this, right? For part B, I already found the antiderivative of this. So not that this is so hard, but I just realized I can just copy my answer from before. It's the same antiderivative. It's just that now I'm not going from 0 to 10. Now I'm going 0 to 1. So I go 0 to 1. I plug these numbers in. 1/3 minus 4 plus 7. And then I'm going to subtract. If I plug in 0, everything is just 0. And then whatever this is 1/3 plus 3. That's 1/3 plus 9/3, 10/3. Okay. Let's do Y. Y was this one. So what do I need to do? I need to do the antiderivative and then plug these numbers in. Of course, this function is the same as it's the same as this function, except it just has this negative sign. In terms of the antiderivative, that it's just going to have the same antiderivative, but it switches the sign on everything. So for the antiderivative, I'm going to write negative 1/3 t cubed plus 4t squared minus 7t. And this goes from 1 to 7, like that. So, oh boy, and this is now, I'm never quite prepared for this, but 7 cubed is kind of a big ugly number, and I want to make sure to check my answer here, so I'm pulling up my program, because I don't trust myself to do it in my head anymore. sorry, just a second. Okay. So apparently 7 cubed is 343. So I get negative 343 thirds. And then this would be 4 times 49, which I can actually do that one. That would be 196 minus 7 times 7, which is 49. And then I'm supposed to subtract what I get from plugging in 1. So what I get from plugging in 1 is negative 1/3 plus 4 minus 7. So, and you can use a calculator on the test, so let me just do this as quickly as possible. 196 minus 49 minus all of this stuff, negative 1/3 plus 4 minus 7. I get that all of this is 36. And then where were we? We were finding x, y, and z. And I still have to find z. So z is this one, so I'm going to find this antiderivative. Of course, it's the same antiderivative as the first one. So I'm going to go 1/3 t cubed minus 4t squared plus 7t. But this one is from 7 to 10, because that's what this is. Yeah, so I plug this in. This is 1,000 thirds minus 400 plus 700 minus, and then I plug in 7. And you'll notice there's some repeat work here. 7 cubed is 343 minus 196 plus 49. So you're going to see some familiar numbers pop up, but we have to do this work. And then this is whatever it is. 1,000 thirds. I can do some of this in my head. Plus 300, and then I'm going to subtract all of this, and this is 343 over 3 minus 196 plus 49. Oh, I didn't do that on purpose. That was 666, apparently. So, right, in the end, sorry, I know that took a long time. Our answer was just x plus y plus z. We broke our original thing into 3 parts, and one of them was x, one of them was y, one of them was z. We found x, we found y, we found z. So my final answer is x plus y plus z, which is maybe I should do this in my head. I feel a little bit lazy about this, but I just want to get to the end here. 2116 over 3. This should be in meters. So that's it. That's the answer. Let me just say a few words about why this makes sense and how to check whether things are, well, making sense. Again, total distance traveled. Distance counts as positive no matter what direction you're traveling. We broke this into 3 parts, and then I had to find my answer for the first part, x, my answer for the second part, y, my answer for the third part, z. Those should all be positive numbers. So one thing you should do is you should check as you go if I got a negative answer for x or a negative answer for y or a negative answer for z, I would know I did something wrong. I didn't, and that's why this makes sense. Right. So then, yeah. So that's it. We can just call this good.